Alright, so today we're going to be working through problem 3.31 from Taylor's Classical Mechanics, and this is a problem on calculating the moment of inertia for a uniform disk using an integral. So they say we have a uniform disk of mass m and radius r, and it's rotating about its axis. And they're saying to replace this sum given up here by the appropriate integral and do the integral in polar coordinates, we should be able to calculate the moment of inertia. So I'll first write down that sum here from alpha equals 1 to n of m alpha p alpha squared. Because we're working in 2 dimensions, we're going to say that our p is equal to r. We can just change everything into r's. So we'll end up with I equals and putting this into an integral form, if the disk is of uniform like it's a uniform disk of a certain mass, we know that there's going to be a density, and this is density per unit area because we're only talking in 2 dimensions here. We're not going with density per volume. So this is mass per area. And we know it's of mass m per area, and it's a disk. So we're going to have mass m per pi r squared. That's going to be our density in 2 dimensions. If we're summing over the disk, we're going to have our density r squared dA, and in polar coordinates this is going to be equal to our density r squared r dr d phi, and we are working our way. We'll go ahead and substitute in our density here. That's m over pi r squared, and we're going to have a double integral for that dA. Because we're working our way around an entire circle, we're going to have phi equals 0 all the way up to phi equals 2 pi, and then we're going to integrate from r equals 0 to r equals the radius of our disk. And we can work out those r squared times r. We're going to end up with r cubed dr d phi. And this is a fairly simple integral to work out. So we're going to have m over pi r squared. When we evaluate that r cubed dr, we're going to have 1 over 4. Substituting in our r and our 0, we're going to end up with r to the 4th. You can confirm this. And then we're just simply going to be left with the integral from 0 to 2 pi d phi, and this is going to work out to squared. I'll combine these terms here. And that's just simply going to work out to 2 pi. Simplifying down, we notice we have an r squared and an r to the 4th. That just leaves us with an r squared in the top. Our m will remain. The pi and the 2 pi will cancel out. We'll be left with a 2 over 4, which is 1 over 2. And this equals the I of our disk, which you may have seen before and not known where it comes from. This is exactly where it comes from, this integral. It's 1/2 mr squared for a uniform disk of mass m and radius r.